Hi, I'm Brian Pease, W1IR, Secretary-Treasurer of the Communications and Electronics section. This talk is about data transmission through a long, single-wire phone line in a cave. During Bill Stone's expeditions to Mexico, he uses single-wire telephone communication from underground camps out to base camp. On the last expedition, Kristen Anderson used USB to UART adapters with Bill's Android tablets that are used for topodroid surveying, and was able to communicate from Camp 1, 1.2 kilometers in the cave, to base camp 1.2 kilometers outside the cave using baseband TTL communications. She used a USB to UART adapter similar to the one shown here, along with software from Google Play called FTDI UART adapter. She tested up to 9600 baud, which is really quite fast. She was unable to coordinate tests at further distances into the cave. There was no man-made or local noise of any type whatsoever, but probably some atmospheric noise and possibly electrical noise from where the wire hangs in waterfalls. Bill Stone asked me if this simple system could be improved to allow data transmission over much longer distances, such as the 3 kilometers to Camp 3, or even as far as 10 to 15 kilometers. The wire in the cave consists mostly of 22 gauge single conductor copper or 2 conductor aluminum or copper and steel field phone wire with the 2 conductors in parallel. 2 conductor copper/steel field phone wire is used from the entrance to base camp, with the ground being a rigging bolt right at the entrance to the cave and not at base camp. My first comment was about the poor grounding. I used Dave Gibson's equation for the resistance between 2 ground rods to model a single 4-inch long rigging bolt, and came up with 1190 ohms in theory in regular limestone, and probably much higher resistance in the real world. I suggested using roughly half a square meter of stainless steel sheet submerged in water with a wire run back to each camp, even if it's a pretty long run. I estimated this would get the resistance down to more like 100 ohms. My next step was to create the simple model shown here of 100 meters of single wire line, so that I could simulate it in the method of moments program NEC4.2. I had to make educated guesses about everything. I assumed the average wire distance from the wall was 1 meter. The size was two number 22 wires in parallel, and average limestone. I ran this model at 1 kilohertz frequency with both an open circuit and short circuit on the far end of the line in order to collect data to create a simple LCR model of the line. I simply strung copies of this simple model in series to create 3 kilometer and 15 kilometer lines. My estimate of the single wire characteristic impedance was about 1900 ohms. Next, I used LT Spice to simulate a 300 baud link on 3 kilometers of single wire plus the 2 kilometer 2-wire line with no defects, that is, leakage to ground and an infinite impedance receiver. Clearly it will work. Next, I tried a tougher test, which was 4800 baud on the same line, but with 5 10,000 ohm loads scattered along the line to simulate bare wires and leakage to ground. The signal is about 2.9 volts peak, and the UART changes state at 1.4 volts, so clearly this will work, even though the rise times are pretty slow at about 57 microseconds. The next higher speed available in the software is 9600 baud, which won't work. The simulated frequency response of the line has a minus 3 dB point at only 4,000 hertz, which Nyquist says should pass 8,000 bits per second in a perfect world. But of course this is not perfect. My next step was to model 15 kilometers of line. Here I changed the poor 1,000 ohm grounds that were simulated in the 3 kilometer tests to 50 ohm grounds, which are what I would really like to see for long distance use in the cave. Clearly 300 baud will work if the line has no leakage to ground. Next, I added 5,000 ohm leakage loads to ground, and then upped the rate to 1200 baud. The signal is about 2.35 volts, which in theory would still work, but probably not in practice. The next higher baud rate available in the UART program is 4800 baud, which definitely will not work. The frequency response of a perfect 15 kilometer line with no leakage loads and a open circuit output at the receiver has a minus 3 dB point of only 1500 hertz, which gives a Nyquist rate of 3000 baud in an ideal world. In reality, the line has series resistance from poor connections, leakage to ground, there's atmospheric noise and waterfall noise, and who knows what signals are picked up at night or from nearby thunderstorms and so on. So I figured that this simple baseband system was not going to work at long distances. I looked into long distance telegraphy from way back in the mid-1800s, which transitioned to a single wire with earth return system very early on because of cost. They used large metal sheets buried vertically for grounding. Some used multi-cell earth batteries, which each used different electrode materials such as zinc and copper, which would produce about 1 volt per cell. And this is a great reason for having all of the grounds be the same material, i.e. stainless steel. They were also aware of telluric currents in the earth, the primary source being changes in the Earth's outer magnetic field that is altered during daylight hours by the solar wind, which is maximum midday. In the US and Mexico, the flow is north-south with positive polarity to the north. The magnitude is typically a few millivolts per kilometer, but can be much higher during solar storms. Some telegraph stations apparently use the diurnal telluric current to augment their batteries. This required a very long wire, There are at least 10 other sources of DC and very low frequency AC ground currents, including lightning and groundwater movement. I spent considerable time trying to design an interface circuit that would do automatic transmit-receive switching, plus allow manual control of DC offset to counter the earth battery and telluric effects, while providing a larger signal, maybe 12 volts, for long lines, all without needing extra batteries. But I have not yet breadboarded that circuit. Next, I thought about using sound card modem software with the tablets to directly transmit and receive sine wave audio frequency modulation using the built-in sound cards. One problem is there's very little Android modem software available. In fact, the only real possibility was a free application called andFlmsg, which incorporates dozens of digital sound card data modes that are used by ham radio operators, along with the ability to send formatted messages with checksums that are automatically saved only if they're received perfectly. The software is intended for portable use by ham emergency messaging services, and unfortunately does not include the general file transfer capability or the ability to break a long message into packets and automatically ask for repeats and so on, all of which is included in the much larger and more complex version for Windows computers. This software can be found as an APK file at w1hkj.com or at sourceforge.net. It is not found on Google Play. Both sources have an up-to-date quick start guide and a user manual. This is an excellent and bug-free program with state-of-the-art DSP modem choices, with digital filtering and some with forward error correction, interleaving, and special coding to avoid errors with weak signal and interference. Most of the modes are centered on 1500 hertz, which is right in the middle of the audio band. A key feature is called RSID, which stands for Reed-Solomon Identifier, which is a preamble attached at the beginning of each message that tells the receiver to automatically switch to the data mode being used for the transmission, and also to correct the frequency, which in our case is not an issue. There is a squelch that prevents the printing of random characters on noise. The software remembers all of its settings when it's shut off, so when you turn it back on, it's just the way it was when you left it. Bill's Android devices have a headset jack for sound in and out. I was able to design a simple passive modem interface to allow two-way communications over a long single wire line with automatic transmit receive switching and adjustable receive level. I included simple high pass and low pass filtering to reduce interference from power line harmonics and from AM broadcast stations, especially at night. The modem output is monaural, so I was able to wire the stereo outputs of the tablet in parallel, which allowed it to easily handle the roughly 8 ohm load. The input impedance of the tablet and most Android devices is 2200 ohms. The little matching transformer steps up the impedance to about 1000 ohms and of course increases the voltage. I actually get 25 volts peak to peak out of my NVIDIA Shield tablet with this interface. The back-to-back diodes protect the microphone input of the tablet during transmit. During receive, there are capacitors both at the line input and the microphone output to prevent DC voltages from forward biasing those diodes. There is also a transient suppression diode on the line to protect the tablet. Normally the receive gain would be set to minimum because the receiver does not need 16.5 volts peak to peak, which is the approximate voltage on the line. There's not much to say about such a simple device. In the actual devices, I used real printed circuit boards, and the cases are actually Lexan polycarbonate NEMA waterproof boxes. In this prototype, you can see the transformer that I used. I was able to find some new old stock units online at a reasonable price for the 10 interfaces that I built for Bill. Having no access to a real underground single-wire phone line, I devised an attenuator to act as a long, very poor transmission line between my two Android devices so that I could compare the performance of the various digital modes in transferring files. I eventually arrived at the odd circuit shown here, which provides a 1,000 ohm match at each end with the ability to add attenuation in 10 dB steps. There's 28 dB of built-in attenuation when the step attenuator is set at 0. I added the Rycom receiver to generate a level of low-frequency atmospheric noise at this audio frequency that we're working at to simulate the real world. These are the results of one of my series of tests to choose the best modes. You can see they're all fairly slow. Minus 68 dB attenuation corresponds to 2.3 millivolts RMS, which is actually lower than the amount of atmospheric noise that I was injecting at the time. Note that I was not testing a long message here. I'm sure if I repeated my short message several times, I would eventually get errors at these signal levels. These 6 modes pass the final test of being able to send an actual long survey data message perfectly with 0 errors at the attenuation levels indicated, while having about 10 millivolts peak to peak of real atmospheric noise on the line. Clearly, the slowest mode, Olivia 16-2000 at 80 words per minute, is the clear winner if your line is really bad. Domino EX88 at more than 7 times faster would be the choice if you have a pretty good line. But if you have a really high signal to noise ratio, the final mode, BPSK 125X12, would be your choice because you're at 2400 RPM, which is also bits per second or baud, and will get your message through fast if there's no problem with the line. Of course, all of this is still pretty much theory and guesswork, and it has to meet the real world at Chevy, hopefully, on an expedition early next year, if it goes. The frequency response of the interface is roughly 400 to 4,000 hertz, which will pass the human voice. This, which gave me the idea to try and use the Android tablets with their built-in microphones and speakers as a high-performance substitute and or backup for the Michi phones that Bill is using. The data modem interface will work for voice as is. All that would be required is a simple Android application that normally listens on the external mic input and feeds the output to the internal speaker, and has a push-to-talk button on the screen that simply switches to the internal microphone and external headphone output when you wish to talk. And I have not found any application that does this. Why should there be, I suppose? Kristen Anderson is looking into creating one. We could have a really big capability for a little bit of software that might be really useful. And it also would provide a very simple way to monitor the line for to see if it's busy or not. So that's all there is. And you can email me with any questions. And also, if you would be interested in helping create that two-way voice application, which we really need.